Okay, so I was just mentioning how the transformations of functions homework, I did not assign to the proper category. So here it is in the proper category, and I want to call it to your attention, and we can do some of these together. So I guess let's write this out on paper, okay? So we can see what we're talking. What are we talking about here? We're talking about we've got a table of values essentially for 3 points in the Cartesian plane, and I just pick them out from the graph as -4, -5. -2, -2, in no particular order, -1, -4. So if our transformation takes the point xy to the point -1/3 x, -1/3 y, as is described here. Now you'll have different parameters, right? So there's a lot of variations on this problem. But that means essentially that the transformation of -4, -5 will be to +4/3, +5/3, right? So it's swapped over into from the third quadrant into the first quadrant, right? And t of -2, -2 will go to 2/3, 2/3, and t of -1, -4 will go to +1/3 and +4/3. So I just need to approximate those transformed points on my graph, right? So 4/3, 5/3, where is that? 4/3 is about 1 1/3, 5/3 is 1 2/3. So I'm going to say that's a point right about there. 2/3, 2/3, I'm going to say that's, it just has to be in the ballpark, I guess, right? So that's about there, 2/3, 2/3. And 1/3, 4/3, that's going to be about there. And then I just complete the thing and click somewhere outside the window and say submit. And it says, yeah, no, that's almost right, but not perfect. Really? Come on. I'm definitely in the ballpark. Oh, yeah, the first point. Yeah, this point here, that should be like over here. I said 4/3, 5/3. Oh no, that was this one, right? Yeah, so 4/3 is a little bit too far to the right, a little too far up maybe. Oh, let's clear all, okay. Try that one more time, see if I can get this right. So you see the outline of the thing is a little yellow. That means that it wasn't terribly happy with my points, which I'm disappointed in my points. Okay, so let's start out with 4/3, 5/3, right? So 4/3, 5/3. I'm going to say that's right about there. 1 1/3 horizontally, 1 2/3 vertically, right? As mixed numbers. Then 2/3, 2/3. I'm going to say that's right about. I mean, there's no sort of way of knowing where my dot is, right? Except to eyeball it and say, yeah, that's about 2/3, 2/3. I'm going to say that's right about there. I don't know, maybe it's too far up. And then, or not far up enough. Let's clear all again. So 1 1/3, 1 2/3. I'm going to say that's here. 2/3, 2/3. What do you think? About there. And 1/3, 4/3. So here's 1/3. I'm going to say that's 4/3. And then to complete the triangle, I get something like that. Let's see if I can get it proper. Yeah, that's all green now. I guess you got to be careful. I mean, because there's a certain margin of error, but it's not huge. So, all right. Questions about that? Am I seeing anything in the chat? Oh, Tia is in the house. And so, good. Glad to have you with us. All right. So, is this all right? So what's happened in this transformation? Well, it's been reflected through the origin, right? So this point at -4, this point, you know, went from here to there. Sorry about all those dots. Let's just move on. I've made a mess of the picture. So leave that page. All right, so we're now on to this page. So match the function with its graph. So this has a vertical asymptote where x equals 4, right? Because that leads to division by 0. And if x gets very large, this ratio gets small. Like if x is 1 billion, can I make this go away and zoom in a little bit on this? Okay, is that easier to see? So if x is 4, then y is undefined. In fact, as you get near to 4, this thing blows up either to infinity or negative infinity, right? Depending on whether you're on one side of 4 or the other. If you're to the left of 4, then this is a small negative divisor, giving you a negative large magnitude number. And if x is a little bit bigger than 4, then this is the reciprocal of a small positive number, which will be a large positive number. As x gets large, like, you know, if x is 1,000,000,004, then this is 1/1 billion, which is teeny tiny. And so we're approaching 5 from above, right? As x gets large, it looks like this is the one, right? We're approaching 5 from above. We're approaching positive infinity. Yeah, this is the one. So how do I choose this guy? Oh, there's a little radio button down here, huh? And now you may have different numbers, right? Yeah, I think you will have different numbers, right? 5 is the next prime numbered problem. And so transform f of x into g of x, where the transformation is shift up 1. All right, so that's easy, right? And I guess we need to draw the line segment connecting them. And submit that, okay. 7, shift down 1, right? So same thing, the dots will be here, and the line segment connecting them looks like this. Let's see if is it okay with that? Yeah, that's good. 11 is the next prime numbered problem. The point -4, -2 is on the graph. Okay, let me go here and sort of move me down out of the way here. And so point -4, -2 is on the graph of y equals f of x. And so these are fill in the blanks, right? So enter a n-tuple or a 2-tuple, I guess, right? So what does this transformation do? This halves the output, right? So the same input will produce half the former output. So if the input was -4, -2, the new point will be -4, comma, -1. Right? If you negate the output, then the input -4 will go to +2, right? If you negate the input, then the point 4 will go to -2, right? So if x is 4, then -x is -4, and we know that f of -4 is -2. So 4, comma, -2. If we shift 6 to the right, that's what replacing x by x minus 6 shifts 6 to the right. So we need a point which is 6 bigger than -4, which is +2. So if x is +2, that's f of -4 is -2. And so the point will be 2, -2, right? Does that make sense? All right. So here we're stretching the output by a factor of 5. So if the input -4 previously was mapped to 2, now it'll be mapped to -2. Now it'll be mapped to -10. All right. And here we're subtracting 12 from the output. So if the input -4 was mapped to -2, now it's going to be mapped to -14, right? 12 less than -2. Let's see if those are all right. Yeah, okay. And just stop me if you got a question. So here's a parabola, and we want to shift up 2 units and then write the new function in the box. Well, they kind of tell you what it is here, right? Using function notation, so I guess we want to write the f of x equals, and it's going to be x squared. The old function was just x squared. We've now shifted up 2, so the new function is x squared. We just sort of copy what they show on the diagram. What are these little buttons? Oh, I see. So you can sort of shift your graph up and down. All righty. Great. But I think that's right. Even though I'm in caps, right? It doesn't care. Caps, lowercase. That was just, somehow I got caps lock on. That was not intentional. The next prime number is 17. The graph of the function 1/72 of f of x can be obtained from the graph of y equals f of x by compressing vertically by 17. Yeah, that's the last choice here, right? So it's a vertical compression by a factor of 72, which means divide the output by 72, right? And there's one more prime numbered problem. Transform by this transformation. So this is compressing. Oh, wait, hold on. No, this is expanding, right? It's confusing for me, right? So x has got to be twice as big for x over 2 to be what it was before. It's one way of thinking of it, right? However, if x is 0, then half of 0 is still 0. So this point on the axis doesn't move. So if I've got my dot chosen, I'm going to want this, but then I'm going to want this one, which is twice as far, right, from the y-axis. So we're stretching away from the y-axis, and we'll have this line segment here. All right. All right, I think those are pretty good problems for understanding transformations of functions. So we can go back to modules, and we were sort of looking at the text, which is here, and we were working on this discovery project. You recall this? And I was kind of searching for my virtual Texas instrument. I still haven't found that sucker. I got it somewhere. It's probably on my website, if nowhere else, but what am I looking at? I want my file system. I was doing a search here. Did I find VTI? No. I don't know where that thing got to. Let me search one more place here. On the C drive, under it's not, oh, I think if I go to documents here, I get what Virtual Studio. That's not Virtual Texas Instrument. Okay. Huh. All right. Well, we don't need it, right? Let's go to GeoGebra to see what we were playing with last time, right? You call this, we were constructing this thing, and what do we got here? Our original function has k times x times 1 minus x, and here k is defined by this slider, right? Shall we make like k equal to 2? It's kind of hard to hit right on it, isn't it? Don't slide too far. Oh no, I've slid too far. I go back and forth, but I can't seem to. Maybe if I give it a little nudge, does that? Oh no, that just zooms. Okay, so 1.99, that's close enough to 2. And then g of x is just the line y equals x, right? So the idea is that you take an initial point A as our input, right? And then you map that to the output on the function. Then you map the output back to the input by taking it to the line y equals x. So this is the new x, which is the old y, right? And this becomes then the second input, right? The second input is the first output. And then that gets mapped to E on the function. And then E gets mapped back to the input here, which is hard to read because it's, yeah. Right, so you see that we're taking the point E horizontally mapped to the line y equals x. So now x equals the old y, right? So this is the third input, and we plug that in, right? So if you look, you know, G is the new. So A is like x naught. D is x1 equals f of x naught, right? Because we've mapped the output back to the input. And then G is f of x naught, which is f of x1, which is x2. So that's the third iterate. Third idiot. Iterate. Iterate means that we repeat this process, right? Of taking the output to the input. And we get to this point H, and then we want to map that back to, so where are these points? So this is A, B, so we don't know how these points got computed anymore, right? So H, do we have a formula for, yeah, right, there it is, right? So if I'm gonna, oh, you can't see that. Let me, can I move it over? Yeah, so if I move it over here, when I double click on, yeah, it's hard to see here, but this little box here, oh no, I shook the box. Don't shake the box. Everything goes away when you shake the box. So let me move it back over here. Somehow I've got to find my stuff over here. Oh, I'm going to exit that, exit this, exit that again over here. Really? Everything is gone? Oh, kind of frustrating. Oh, I think it's this tab. I was clicking on the wrong tab. So if I put that one back up there, I can see what I had. And then bring this back. Oh, so redefine. So I've now lost what that was, but I can double click on this again. And if I bring it over here, it's kind of small. I can't see what we're seeing anymore. So let me fix all them. All my windows went away. Don't shake your windows in Windows because you'll be sorry unless you really want that result, which I didn't. Okay, so you see this little box here? This is what happens when I click in GeoGebra on that point. So this is how this point is defined, right? And I don't know what that H is doing there, but can I? Oh, I want to choose all this, copy and paste it, right? And then cancel that. But then if I come back over here, let's get back to my GeoGebra window. And we'll be done with this soon. I know this may be hard to be patient for, but if I then cut and paste that old one in here, I can just say, yeah, keep iterating, right? So that means f of whatever this was is the new input, which was the old output, and then compute the new output from that new input, right? And you get to that point there, which I think what I want then is this is my x value, and that is my y value. Oh, we got, yeah. So then that plots that new point J down there. And it's a little bit hard to see what's going on because our K is not convenient for this. So if I, yeah, right, what's going on? So this J, I don't know where that J is coming from. Yeah. Yeah, I think that maybe that J is just a mistake somehow. Yeah, the X value and the Y value should be 0. So what is J doing up on the curve when, or maybe it's not on the curve. Is that a J or is that an I? I think that's an I, huh? So this is taking the old output as the new input and then producing, right, because I didn't draw the point on the curve. So let me do, sorry, on the line y equals x. Sorry, this is probably very confusing. I apologize for that. Let me paste this in and say, I want this point where the input is equal to the output. Right? And then I can finish my line drawing, right? So I want the line, am I in the wrong? Okay, I want the line so you don't see the menu, huh? And then I want to connect this point to that point, and then this point to that point, to that point. Yeah, you can see what's going to happen here. It's going to wind around and converge, right? And that's, you know, for different Ks, you get sort of a different behavior, right? Can we make, so there's a threshold where K kind of goes, makes the process go haywire. That's why there's this chaos thing going on, right? So we keep mapping the output back to the input, and then, you know, I could do a few more iterations of this, but let's just move on. This is kind of interesting, but it may be, you know, a little esoteric. It's a project. Andre Mejia, I hear you, and let me give you a little, and Tia, okay. Right, we already got Tia. Mejia is here. Make a record of that. Save. Okay. So, all right. Let's get back to the text and make some tracks. So the text is here. And so we kind of talked about the Discovery Project, perhaps indulging a little bit in GeoGebra. So all right. So yeah. So using graphical addition, yeah. So if you look at the graph, so you've got f of x is what is it here? They don't have a formula for it. It's just given by the curve, right? And g of x is this straight line, right? So when you add the two things, well, if f of x has a 0, then you're adding 0 to g of x, and you're on the curve g of x right here, right? Then the sum of the two curves, right? You got, you know, this length plus that length, right? So that you add the two y values, right? And you get a y value up here. So the purple curve is the sum of the blue and the red curves, right? It's the sum of the y values. All right. Composition. All right. So this is sort of the more important thing, right? This is kind of what we were talking about with the iterative process. We kept on feeding the output back to the input, but you can take the output of any function as the input to another function, right? So is that too small? Let's make it a little bit bigger. So here, h of x is the composition of f with g. So first you plug into g, then the output of g is the input to f. Is that clear? So if g is the function x squared plus 1, and f is the function square root of x, then the output of g is the input to f. And what does f do to its input? It takes the positive square root. Right? So that's the composition of those two functions written as a single function formula, right? And the idea is here, right? You first plug into g, then you take the output of g as the input to f, and you get the output of f. So let's see, what are we doing here? Okay, so in general, given any two functions, f and g, we start with the number x in the domain of g and find its image, that is its output, g of x. And if this number g of x is in the domain of f, then we can calculate f of g of x. But so that's two requirements. One is that x is in the domain of g, and that g of x, the output of g, is in the domain of f. Then you get a value, which is f of g of x, right? F composed with g. That's actually, I think of that as an O, right? Of. All right, and so there's a definition. It's called the composition. And arrow for f of g, right? So kind of thinking of, the domain of g is this blue set of values here. The image of that domain under the action of g is this purple area here. And the domain of f, well, the hope is that the image of g is contained in the domain of f, but that may or may not be true. So we don't really see the largest domain of f here. We see that if j of x is in the domain of f, then we get f of g of x. And yeah, this little arrow diagram, take it or leave it. Finding the composition of functions. Okay, so this is something you like. So with real numbers, what are the operations? Addition, subtraction, multiplication, division. We can also do addition, subtraction, multiplication, and division with functions, right? We just take their outputs and add them, subtract them, multiply them, or divide one of them by the other, right? What we can't do with numbers that we can do with functions is this composition thing. So compose one with the other, right? Take the output of one as the input to the other. So, given a function, sometimes you want to decompose it as a composition of simpler functions. Yeah. Yeah, so they give you a few examples. Maybe are we ready to go to the exercises? Composition of three functions. Yeah, that's just a little bit more complicated. Recognizing a composition of functions. Applications of composition. Well, let's see, what do they say here? When working with functions that model real world situations. What is this real world I keep hearing about? My mother told me, advised me, cautioned me repeatedly. It still does. You should be living in the real world. No, I think that meant get a job. But for our purposes, we're sort of thinking, the physics of the real world. What happens in the real world of things, right? What sort of situations do we have? So often to model those processes, we introduce variable names to say, well, let v equal the speed of the car at time t, where v is measured in feet per second and t is measured in seconds, right? So we can then model the motion of the car or its velocity with that function. For example, if air is being pumped into a balloon, then the radius r of the balloon is a function of the volume v of air pumped into the balloon. Yeah. So r measured in cubic meters, maybe. Volume is measured in cubic units of length. Oh, sorry, r is the radius of the balloon, and v is measured in cubic units. I got that backwards. So we take the volume of the balloon in cubic units and produce the radius of if it's a spherical balloon, presumably has some radius, right? And so here they give you an application where a ship is traveling in the night. No, they don't say in the night. Maybe it's during the day. At 20 miles per hour, parallel to a straight shoreline. The ship is 5 miles from shore. It passes through a lighthouse at noon. It passes a lighthouse, not through it, right? That would be a mistake. At noon. So we want to express the distance s between the lighthouse and the ship as a function of d, the distance of the ship has traveled since noon. Oh, that is, find s, which is the distance between the lighthouse and the ship, as a function of d, the distance the ship has traveled. Okay, and then we want to express d as a function of t, the time elapsed since noon, and then we want to compose those to get s as a function of t. And for the distance, we need to sort of draw a diagram. So does that look like a right angle there? Yeah, I guess if you viewed in perspective, right, that's a right angle. So we're sort of viewing this from afar and not right above, right? So we're viewing at an angle. And so looking down at a right triangle from an angle, the right angle does not appear to be 90 degrees, but they put that little right angle indicator there, indicating, yes, that's a right angle. So this is a right triangle. And the distance of the ship from the lighthouse, is that at noon, is 5 miles. Is that what they told us? The ship is 5 miles from shore, and it passes a lighthouse. So it's traveling parallel to the shore. So at noon, the ship is here directly opposite the lighthouse and a distance of 5 miles from shore, so a distance 5 miles from the lighthouse. As time goes on, the ship travels parallel to the shore at a certain speed, but so it travels this distance d, and we can solve this right triangle for s, right? S squared equals d squared plus 5 squared. And so they've got s is then the square root of 25 plus d squared, which is here, right? So that's the distance from the lighthouse as a function of d, the distance the ship has traveled. And then we're going to say, well, the ship is traveling at a constant speed of 20 miles per hour. So we can say the distance the ship has traveled is speed times time, where t is in hours, right? 20 miles per hour times t hours will give us the number of miles the ship has traveled. And so then if we compose f with g, we get f of 20t, which says due to 20t, what was done to d, where d was squared. So we're going to square 20t, and we'll get 400t squared, although they don't bother to expand that there. All right, we're into the exercises. And I think, is that the section on composition of functions? Okay, so let's look at these exercises first, and then we'll look at the homework related to those. And can we go by steps of 4, maybe? Let's do steps of, so we'll do every 4th problem. Oh, except that this one is sort of a so problems 1 through 4 relate to the same graph here, right? F plus g of 2, that's going to be 3 plus 5 is 8, right? Just add these outputs, right? f minus g of 2 is going to be 3 minus 5 is negative 2. F times g of 2 is going to be f of 2 is 3 times f of g of 2 is 5. That's 15 here, right? And, similarly, we can divide. Let's move on to number 8 here. And combining functions. Find f plus g, f minus g. So these are pretty straightforward, and they're domains. So the domain of g, well, let's go ahead and write this out. All right, paper and pencil time. Uh-oh, here we go. This is, what section is this? 2.7 or something? They're going to tell us here. 2.7, right. And 2.7, number 8. And we see f is x, and g of x is square root of x. So here, this just maps the input to the output, right? And g of x says the output is the square root of the input. And so f plus g. So here, let's write out what the domain is, right? In fact, let's write out both the domain and the range. So the domain here is all real numbers, and the range is all real numbers, right? This R with a double bar indicates the set of all real numbers. Whereas here, the domain is the interval from 0 to infinity, and so is the range, right? So because we're taking the positive square root, the output has got to be positive. So the smallest the input can be is 0, and that's also the smallest the output can be, right? But the output can be as large as you like. Take a number large enough, you can make the square root as large as you like. So f plus g of x, that's just going to be x plus root x, right? And the domain is going to be the same as the domain of g, right? Because that's the smaller one. It's got to be in the intersection of those two things. And so that's equal to the interval from 0 to infinity, right? In order for this sum to be defined, the square root of x has got to be a real number. Same thing with f minus g, right? How about f times g of x? Well, that's x times the square root of x, and you got the same thing, right? Same domain. In order for this to be a real valued expression, x must be greater than or equal to 0. So how about f divided by g of x? Well, in that case, we've got x divided by the square root of x. Be careful here, right? Because at 0, we've got 0 over 0, which in general is indeterminate. And so not well defined, right? So what happens if we say f divided by g of 0? Well, then we have 0 divided by the square root of 0, which is 0 divided by 0, which is not a real number, not a number. That's sort of computer notation for that. 0 divided by 0 is not a number. Not a number. Even though, right, we can think of this as the square root of x, right? X divided by the square root of x is the square root of x. So this is defined at 0, but f divided by g is not, because of how we get to it, right? We get to it by taking the ratio of outputs, and the ratio of outputs is going to be, it's a subtle point, but so the domain here we have to restrict to the set of all strictly positive numbers, right? You can't have 0 in the divisor. So even though the simplified expression, in fact, I would say this, right? F divided by g of x is equal to square root of x if x is strictly positive, not a number if x is equal to 0, and not an element of the set of real numbers if x is negative. You can do weird stuff to the paper by pinching it, huh? Okay. Questions about that? I'm not paying attention to the chat. Okay, Santi is here. Maria has said something. Do more book examples instead of real world examples. Yeah, right. That was with a laughing out loud. Because yeah, I know the real world is a messy place. But you know, people often ask, what's this all good for? Why all this abstraction? Well, the abstraction is all about modeling, right? We try to, you know, well, some of us are perfectly content with pure abstraction, right? For instance, myself. But others feel an itch to apply those abstractions in some sort of useful way, which is understandable. Okay, so I've got Santi, and I'm also hearing from Carla. Did I not hear from Carla before? I thought I did. Oh, I didn't. Okay, right. Right. So, all right. So, any questions about that? So let's get on to the compositions, right? Because that's the more sort of interesting thing you can do with functions that you can't do with real numbers. Oh, this is that, and I want this. Okay. So let's see. 12. It's going to be over here somewhere. And what are the instructions here? Oh, I have to scroll down here to read the instructions. Combining functions, find the sum, difference, product, and quotient. Okay, so same thing in 12. Okay. Sure, let's go ahead. So, so here's number 12. I guess I'll move me up out of the way over here. Okay. Yeah. Okay. 12, we got f of x is x squared plus 2x. And g of x is 3x squared minus 1. Okay. So the sum, you're just going to combine like terms, right? You get, 4x squared plus 2x minus 1. The difference, yeah, again, just combine like terms. The product and the domain and the range for both of these are all real numbers. Oh, hold on. Not so. The domain is all real numbers, right? So the domain equals the real numbers here. The domain equals the real numbers here. The range, for that, you've got to determine where is the vertex and does it open up or down, right? Well, the rule for the vertex is h is negative b over 2a, so that's going to be negative 1. And f of negative 1 is negative 1. So and it opens upwards from there. So the range is going to be the interval from negative 1 to infinity for f. What about for g? Well, here the vertex is at x equals 0, right? Because b is 0. Negative b over 2a is going to be 0 over 6, which is 0. And g of 0 is -1. Okay, so this has the same range, right? You can get -1 by plugging in 0, and that's the smallest output you'll get, and the other output will be bigger. All right, so the range of both of these includes 0. So if you've got f over g of x, the domain is going to be what? Well, you can't have so what input produces a 0 output for this function? Well, there are two inputs that produce a 0 output, right? If you factor it, you see that, sorry, the problem is with g, right? If the output of g is 0, right, because we have f divided by g, if g has a 0 output, then we have division by 0, right? F divided by g, and we're dividing by g. If g is 0, then we're dividing by 0. So we want to rule out the possibility that g can be 0, and that's plus or minus the square root of 1 over 3. Right, I didn't leave enough room for this. Let's go ahead and rewrite it on another sheet here. So with these functions, we've got f over, and I can then spread this out a little bit, right? So this is going to be 2x squared. What was it? Plus, oh, sorry. X squared plus 2x, and on the bottom we have 3x squared minus 1, right? So again, we want to limit the domain so we don't have division by 0. So we need to say the domain is the set of all x such that 3x squared minus 1 is not equal to 0. In other words, the set of all x such that, so solve the equation where it's equal to 0, and you'll have x not equal to plus or minus the square root of 3 over 3. Is that? I've skipped a step there where you have the square root of 1/3. Let's put it on the side here, right? So the square root of 1/3 is 1 over the square root of 3, and you can multiply the top and the bottom. It's called rationalizing the denominator. And so on the top, you get the square root of 3. On the bottom, you get root 3 times root 3 is 3. And we want positive and negative, so there's 2 points. So that's going to be the interval from -infinity up to, but not including, the negative square root of 3 over 3, union with the interval from negative square root of 3 over 3 to positive square root of 3 over 3, so in between the two zeros, and then the interval from positive square root of 3 over 3. All right, so you got 2 holes in the x-axis where there is no output for those inputs. Okay, let's move on to number 16. So here's number 16. We got a couple of functions. And still we're dealing with just sums and differences and quotients, and the bigger problem is with the quotient, right? So, or here we got a problem because the domain is not all real numbers, right? If x equals -1, we got division by 0, so -1 is not in the domain. So the domain is going to be equal to the interval from -infinity to -1, not including -1, and then from -1 to infinity, right? How about the range? Well, you can never get 0 as an output. Is that obvious? All right. So the range is going to be everything. You can get any other value except 0, right? Because the numerator is always 2, right? In order for a ratio to be 0, the numerator's got to be 0. So you can get as close to 0 as you like by taking a very large x, right? How about g of x? This is x divided by x plus 1, which you can do long division. X plus 1 goes into x once. You get a remainder of -1. So this would be 1 minus 1 over x plus 1. To check that, get a common denominator and combine the numerators over the common denominator, you have x plus 1 minus 1 is x over x plus 1, right? And so here the domain is equal to, again, the same domain, right? Because we have, the same divisor. So negative 1 is not in the domain, but the range now, you can't get 1 as an output, right? There's no input that leads to this being 0 because the numerator is fixed at 1. So the range is the interval from negative infinity to 1 together with the interval from 1 to infinity. All right. What about, so there's, for f plus g is just going to be the intersection of the domains, which is the same. There's the same domain, so their intersection is just that. Same thing with f minus g and f times g. How about f divided by g? Well, for f divided by g, we need x to be in the domain of f and g. Well, first of all, shall we write out what that is? That's going to be, and f is 2 divided by x plus 1. G is x divided by x plus 1. And so you might say, well, that's, the x plus 1's cancel out, right? So that's 2 over x. Is that algebra clear? You can multiply the top and the bottom by x plus 1. Of course, that requires that x plus 1 is not 0. Otherwise, you're multiplying the top and the bottom by 0. And that's true if x equals negative 1. So the domain here is, obviously, x can't be 0. Not so obviously, x can't be negative 1. So the domain is the set of all x such that x is not 0. That's clear because, when you simplify this, you get 2 divided by x. What's not so obvious is x can't be negative 1 because the formula says, first plug into f and g, then do the division. But if neither f nor g is a number, then you can't do the division. Not so obvious, huh? All right. So are we going to ever get to compositions here? Let's go back to the book. Yeah, time is a wasting. Find the domain of the function. So there's a lot. I'm going to skip on to where we get some more interesting compositions, right? Evaluate compositions. Okay, so so here are two functions. We got a linear and a quadratic, and we want to form the compositions. So let's just do that in general, huh? And then we'll see about these particular values. Okay. So let's say this is 2.7 numbers 27 through 32. We'll pick out a few of these. We're not going to do them all. So f of x is a linear function with slope 2 and intercept negative 3. And g of x is a quadratic with a difference of squares, right? 4 is 2 squared. And so that's 2 squared minus x squared. So we could factor that as 2 minus x times 2 plus x. But is that what we want to do? Well, let's compute f of g of x. I just substitute for g of x 4 minus its formula, right? And then do to that what f says to do to its input. F says multiply the input by 2 and subtract 3 from that product, right? So I'm going to say 2 times the input minus 3. All right, and then we clean up a little bit and we write this as 8 minus 3 is 5. So combine those like terms, and then minus 2x squared. So that's a simplified formula. What's the domain of that thing? Well, all real numbers, right? There's no restriction as to what you can plug into F. The range of F is also all real numbers. You can get any output you like by choosing the appropriate input. Domain of G is all real numbers. The range of G is all numbers up to, but not, up to and including 4, right? But 4 is the largest output we can have because we're subtracting this positive number from 4, or this non-negative number, right? So the domain of G extends up to 4. So that's interesting. So I guess the largest output F of G can have is going to be 5. Oh, yeah, then that makes sense in terms of this formula, right? So the range of F of G is all real numbers up to and including 5, but not anything larger than 5, because we're subtracting this positive number from 5, right? Or we could be subtracting 0 from 5. Is 0 a positive number? Yeah, maybe sometimes. All right, so F of G of 0, now it's just going to be 5, right? And we could say, what's G of 0? That's 4. Oh, that's a good point, yeah. G of 0 is 4, and F of 4 is 5, right? So that we could just plug directly into this thing, right? How about, let's do G of F of X, right, by contrast, right? So that says, take the output of F and plug it as the input to G. So the shorthand for that is just to write the output for F as the input to G. And what does G do to its input? It squares it and subtracts that square from 4. So it's going to be 4 minus the square of 2x minus 3. All right, now expand and combine. And leave it in parentheses for simplicity's sake, because otherwise you got too many negatives running around at the same time. So the square of this is going to be 4x squared. That's the square of the first term. Twice the product of the 2 is going to be minus 12x, right? You have 2 negative 6x terms. They combine to negative 12x. And the square of the second is 9. And so when the dust clears, that's negative 4x squared plus 12x, right? Everything in here is negated. And you got a negative 9. 4 minus 9 is negative 5, right? All right, so what's the range of that? The domain is all real numbers again, right? There's no restriction on what can go into F, and you get all real numbers coming out of F. And so you're getting the range of G. And we know the range of G is all numbers up to including 4. Is that going to work here? So let's go ahead and complete the square for this, because that'll give us practice completing the square. So the steps are factor out the leading coefficient, right? And then balance the equation. So what goes in this blank spot? Well, inside here we got the leading coefficient is 1. So inside the parentheses we can complete the square by adding the square of 3/2, right? So that's 9/4. But everything inside the parentheses is multiplied by negative 4. So 9/4 times negative 4 is negative 9. So we need to add 9 back in to balance the equation, right? So this plus 9 balances the effect of adding this square in here. And then we write it in nice vertex form as x minus 3/2 squared minus 4. And look, the range is again, plus 4, sorry. It's just what we expected, right? All real numbers up to and including 4, nothing larger, right? Okay. And the domain is all real numbers. Okay. So how are we doing here? I'm probably taking too long with all of this, right? It's t minus 2 for terminating time. Oh, well, let's move on. Solving an equation for unknown function. This is number 74. All right, let's give it a try. We got 2 minutes. And then tomorrow we'll get to inverse functions, okay? Sorry we didn't get there today, folks. But you do have your composition of functions homework available. And I can extend the deadline on that if you need it. Let me know. What have we got?
Yes, please.
Yeah, okay. 74. G of x is a linear function again. Oh, there's a lot of these, huh? And h of x is a quadratic, sort of same kind of setup. 4x squared plus 4x plus 7, a little more complicated looking. Find a function f so that h of x is f of g of x. That looks like a challenge, huh? So in other words, maybe we put the f of g of x. So we don't know what f is, right? But whatever it is, it's got to take g of x, which is 2x plus 1, and produce 4x squared plus 4x plus 7. Well, guess and check. What would a good guess be here? Well, look, here's the input, right? There's the output. If we square 2x, we get 4x squared. So it looks like a good start would be to square the input, right? So if we say that f of x start out with just x squared, then f of 2x plus 1 would be the square of 2x plus 1, which would be 4x squared plus 4x plus 1, right? Just squaring that binomial. And that's almost what we have, right? We got the 4x squared plus 4x. We just don't have the 7. We got a 1 instead. So just add 6 plus 6. Then we're done, right? So that'll do it. Guess and check, always a solid method of attack. Okay, it's 12:11. We're a minute over. Any questions before we quit? Yeah, and I can extend this deadline. How do I do that? Yeah, it's a mystery to all of us. Okay, let me see. Composition of functions. I can put enter here, and then I go here and say settings. It says it's set by your LTI or your canvas, right? So I can't do it there. So I have to go back over here and say edit. I'm just about edit. Okay. I just keep having this same stupid problem. So is the problem that it's not a homework assignment? It is a homework assignment, right? If I try to edit it here, I don't get a choice to change anything like the due date. If I enter in here, I can edit its LTI, but then it just tells me, no, you got to go somewhere else for that. This is driving me nuts. I thought I had this figured out. Usually I get like a thing that says, edit the settings here. All right, I'll figure it out. I'm going to stop the recording.